Hello, good morning, good afternoon, good evening. This is STAT 248, Couplings and Monte Carlo. And this is the fourth video of the course, corresponding approximately to the second half of the second chapter of the lecture notes. The topic of today is common random numbers, optimal transport couplings, and the relationship with the Wasserstein or Kantorovich distance between probability distributions. We'll see that those couplings, so common random numbers couplings or optimal transport couplings, which we will see sometimes are the same thing, are related to Monte Carlo methods in multiple ways. They come up naturally when we talk about variance reduction, and they're also very much related to inverse transform sampling in the one-dimensional case, and they provide paths towards multivariate extensions. And also, they are related to the Wasserstein distance, similarly to the maximal couplings being related to the total variation distance. And so we'll see this other big family of distances between probability distributions, which will be useful in the rest of the course. So let's talk first about variance reduction and how those common random numbers arise. So in the previous video, we looked at couplings, so pairs of random variables x following p and y following q, and couplings were simply joint distributions of with marginals p and q. And we've seen that some couplings were special. They were always the independent coupling, but there were also other couplings, such as the coupling maximizing the probability that x is equal to y, which was called the maximal coupling, and we've seen it was related to the total variation distance. So next, we'll look at other couplings, and we can think of them as the couplings that maximize the correlation between the variable x and y. So the correlation defined as the covariance between x and y divided by the square root of the variance of x times the variance of y. The covariance itself can be recalled briefly, so it's the expectation of x minus the expectation of x times y minus the expectation of y, which we can expand to obtain this as the expectation of x times y minus the expectation of x times the expectation of y. That's the definition of the covariance between x and y. And so maximizing the correlation, given that the marginals p and q are fixed, is exactly the same as maximizing the expected product of x and y. The other quantities, the expectation of x, for example, is given by the marginal distribution p. So here we're only acting on the relation between x and y. So note also that the expected distance between x and y can be expanded as the expected square of x plus the expected square of y minus twice the expected product of x and y. And thus, maximizing the correlation, which is maximizing the expected product, is also equivalent to minimizing the expected distance between x and y, square distance, I should say, between x and y, given that the marginals are fixed. And so this, in fact, will be seen as a particular case of a so-called optimal transport problem. So the topic of this course, this video, is the optimal transport problem. And we will see that the couplings associated with this optimality are related to a certain distance between probability distributions called the Wasserstein distance. But first, let's motivate why we might want to maximize the correlation between x and y, or the covariance between x and y. Why would we care about trying to maximize this quantity while keeping the marginals fixed? Well, a typical scenario in the context of Monte Carlo is that we might be interested in the difference between the expectation of x and the expectation of y. So we're interested in the expectation of x minus y. So we might assume that we can sample x from P and y from Q, perhaps many times, and average the difference. And then we'll be interested in the variance of the difference, which is the sum of the variances minus twice the covariance between x and y. And so if we want to minimize that variance, then we want to maximize the covariance between x and y. So we'll be able to estimate the difference in expectation between those two variables with more precision if we're able to induce positive correlations between x and y. So this is in a plain Monte Carlo setting, but we can also look at the context of Markov chain Monte Carlo. And there's a similar idea that can be implemented, for example, proposed by Radford Neal and Pinto in a technical report available online. There's a reference in the lecture notes. So assume that we have a Markov chain X that converges to distribution pi. Assume that we want to come up with the estimator average of evaluations of a function h at xt. That would converge, under regularity conditions to the expectation of h with respect to pi, the limiting distribution of the chain. So the idea might be to introduce another chain, denoted by y, a Markov chain as well, this one converging to another distribution, denoted by g. For example, we can think of g as an approximation of pi. But we will choose g to be a distribution that we know the expectations of. So we will assume that the expectation of h with respect to g is known analytically, so we can compute it without any error. So in that case, we can come up with a new estimator for the expectation of h with respect to pi, which is the original estimator minus some beta times the difference between the average of h with respect to the Markov chain y minus the expectation with respect to g. So this will converge still to the expectation of h with respect to pi, because the term on the right hand side goes to 0. This difference goes to 0 as t goes to infinity. And then we can think of choosing beta optimally to reduce the variance of this new estimator. We can compute the variance as a function of beta. It's a quadratic function, and we can optimize it, so we can find the beta star that minimizes the variance of the new estimator, and it will be given by basically the covariance between the average over the two chains, rescaled by the variance of the first chain. And so, provided that we can introduce positive correlation between the two Markov chains, we can obtain a new estimator which can have a much smaller variance. There are quite drastic variance reductions in the paper by Neal and Pinto. So we can reduce variance by introducing positive correlations, both in the standard Monte Carlo setting and in Markov chain Monte Carlo. So the natural question is, how do we actually introduce positive correlations between two random variables, x following p and y following q? Of course, it will depend a little bit on the context. So it will depend exactly on how we intend to generate those two variables in the first place. So let's look first at the simplest case, where the random variables are drawn from algorithms that rely on some random input. So we assume that x is obtained as the output of an algorithm that also employs as input random variables denoted by u, for example, a uniform variable in the interval 0, 1. So then we can write x as a function of u. And likewise, suppose that the variable y following q is obtained from an algorithm that take also a random input of the same format. So we can write, for example, y equal g of u. So you might know at least of one case, and that's the case where x and y are obtained from inverse transform, so an inverse CDF transform of uniforms. Then they are written as deterministic functions of a random variable, which is uniform. And so in that case, the natural idea would be to use the same random variable u in the generation of x and of y in order to introduce correlations between x and y. So that's what's usually called common random numbers. Now it's not always applicable. So the hard case would be if x comes from another algorithm that does not depend on the fixed random variable u, but instead might depend on an infinite sequence of random inputs, u1, u2, and so on. So an example of that is a rejection sampler. There's a while loop in the rejection sampler, and thus you cannot define this as a deterministic function of a fixed dimensional random input. So if you have two rejection samplers targeting two distributions, you can try to feed to the two algorithms the same sequence of random variables, but they might not eventually employ the same exact number of random variables. And so this strategy might not induce much correlation. It might or it might not. So for the rest of this video, we'll focus on methods that are similar to inverse transform, where we can define the variables x and y as a deterministic function of some random input. And we will call common random numbers the strategy of providing the same exact input to the two algorithms. So to sum up, common random numbers is a strategy that makes sense if we specify a sampling mechanism that would transform random input denoted by u into the variable x and the variable y. And then we talk about common random numbers if we provide the same random input when generating x and generating y. So again, a big example that we will use in this video is the one-dimensional case where x and y are in the real line, and we can define x as the inverse CDF transform applied to u, and y as the inverse CDF transform applied to the same u, but for the CDF of y. And u is a uniform in 0, 1. So we said that this might induce positive correlation between x and y, but in fact, what is remarkable and far from obvious is that this induces the maximal amount of correlation between x and y. So over all possible ways of coupling the variables x and y under the marginal constraints that x follows p and y follows q, common random numbers fed to the inverse CDF is in fact the way that maximizes this correlation. And in fact, it maximizes the expected product of f of x, g of y for any pair of increasing functions f and g. So not only the product of x and y themselves. And in fact, slightly more generally, the result is usually phrased as the maximization of the expected psi of xy, where psi is a function of two variables, two vectors of variables potentially, called supermodular. So this satisfies a certain property that makes, for example, a product of two functions f of x, g of y a particular case. So you find more on this in the review article by Glasserman and Yao in 1992. The result that dates from the 70s. So in fact, common random numbers in this above case can be in fact the optimal thing to do, the optimal coupling for inducing correlations between x and y. Now often it might not be the optimal thing to do, for example in different settings, in multivariate settings, but it will very often be a reasonable thing to do. And so we will see in the later chapters a lot of common random number strategies that are not necessarily optimal, but sensible strategies. So let's comment a bit more on this strategy of common random numbers with inverse transform. Again, x is defined deterministically given u and y as well. And thus we can go from x to u deterministically. And thus we can write y as a deterministic function of x as fy minus 1, so the inverse of the CDF of y, evaluated at the CDF of x evaluated at x. So it's the composition of two functions, an inverse CDF and a CDF evaluated at x. So under this coupling strategy, the variable y is obtained as a deterministic function of the variable x. So in fact, we can look at this as a particular choice of function that minimizes a certain criterion, and that's called the Monge problem. So the Monge problem looks like the infimum over all functions t, such that the push forward measure of p through t is equal to q. We'll go back to that. Of the expected square difference between x and t of x. So that's the expected distance, square distance between x and the image of x through the map t. We want to minimize that expected distance under the constraint that the distribution of t of x when x follows p is equal to q. That's called the push forward measure obtained from t and p. So the objective itself can be understood as a cost of moving the point from location x to the new location t of x when applying the map t. And thus the terminology of transport. This is called an optimal transport problem, and it was formulated by Gaspard Monge in the beginning of the 19th century, literally as a problem of transporting some goods from some locations to other locations. And so what we've seen before with this common random number strategy and inverse transform is that in fact when p and q are continuous distributions, it happens that this optimal transport problem has as a solution the map fy minus 1 composed with fx. And that's called the optimal transport map. There's a vast and very interesting literature on optimal transport problems. A very good and recent account is in the book of Perret and Couturi called Computational Optimal Transport, which is freely available online. I highly recommend it. So now we've seen some connection between common random numbers strategies and optimal transport. So the Monge problem is an interesting optimal transport problem, but it does not always have a solution. In fact, it is usually a big question whether it has a solution or not. So for example, if the distribution P is supported by n atoms, x1 to xn, which means it's a discrete distribution and the values of the variable are in the set x1 to xn. So we can write P as a sum of weights summing to 1 times Dirac mass at xi. Then if that's the distribution P, and we introduce a map T, then of course if x follows P and we apply the map T to x, we can observe at least n distinct values, possibly fewer than that. Could be anywhere between 1 and n values. And in particular, this means that T of x, the random variable T of x, cannot be distributed according to a distribution Q if Q has more than n atoms, or of course if Q has a continuous part. If Q is a Gaussian, it takes infinitely many possible values, and so it cannot be obtained as T of x, where x follows a distribution with only n possible values. And so a classical way of relaxing the Monge problem to allow the existence of solutions in much greater generality is the so-called Kantorovich relaxation, or the Kantorovich transport problem. And it's defined in terms of couplings this time, instead of a definition in terms of maps. So we introduce the infimum over all couplings of the distributions P and Q of the integral of x minus y squared with respect to the coupling gamma. And of course, this integral, we can recognize it as an expected squared difference between x and y, where the pair xy follows the coupling gamma. And this is more general than the Monge problem, because now it can be defined for discrete and continuous solutions. It could even be that P is discrete and Q is continuous. And we might still have couplings of those two distributions. And thus, among the couplings, we might have a coupling that attained an infimum. It might not be unique, but there might be at least a coupling attaining the infimum. Of course, note also that the objective itself takes non-negative values, so it's lower bounded by 0. We do need conditions on the variables. In particular, we need the integral to be finite, and that means typically moment conditions on the distributions P and Q. We'll see that again a bit later. So let's try to visualize a little bit the Monge and Kantorovich problems on a simple example. The state space is the plane. We introduce x1, x2, 2 points on the plane. And we introduce y1, y2, and y3, 3 other points in the plane. And from those points, we define 2 distributions. The distribution P is a weighted sum of x1 and x2, Dirac masses at x1 and x2. So the distribution takes either the value x1 or x2 with probability half-half. And likewise, we define Q as an equally weighted sum of Dirac masses on y1, y2, and y3. So from those 2 distributions, we can see that we can choose any function t that maps x1, x2 to any of y1, y2, y3. And the variable t of x, where x follows p, can only take at most 2 different values. So in particular, t of x cannot follow the distribution q, however you choose the function t. So the Monge problem has no solution here. And if you do it the other way around, in fact, here you cannot find a solution either, because if you find any function s from y1, y2, y3 to x1, x2, then s of y, where y follows q, in fact, cannot follow the distribution p. For example, if we look at the probability that s of y is equal to x1, well, it could be 0, it could be 1/3, it could be 2/3, or it could be 1. But it cannot be 1/2, because you cannot obtain 1/2 as the sum of thirds. And thus the Monge problem has no solution in either direction. So if you give yourself those two distributions, you cannot define the Monge optimal transport problem. And hence the appeal of this relaxation by Kantorovich, which will have a solution in this case, as we'll see next. So in the Kantorovich version of the problem, we introduce couplings of the two distributions, P and Q. And so the couplings here can be represented by a 2x3 matrix. First row corresponds to x1, second to x2, the columns to y1, y2, y3. And the constraints, the marginal constraints, mean that the columns must sum to 1/3, while the rows must sum to 1/2. And there are always such matrices. For example, here we obtain from the independent coupling the matrix with entries all equal to 1/6, 1/6, satisfies the marginal constraints. And of course, there's also other matrices satisfying those constraints. And the objective of the Kantorovich problem is the integral of x minus y squared with respect to gamma. But here in the discrete case, we can write this as well as a sum over I and j of xi minus yj square times the entry gamma ij of the matrix gamma. So we can imagine pre-computing Cij equal xi minus yj square. We have 6 possible values. And so having this matrix of the cost associated with the pair ij, the goal is to minimize the sum over all ij of Cij times gamma ij. Minimization is over gamma under the constraints. So we need to respect the sum of the rows being equal to the weights in the distribution P, and the sums of the columns being equal here to 1/3, 1/3, 1/3. And so you see this optimization problem is not too scary in gamma. It's in fact a linear program. The objective is a linear function of gamma, and the constraints are linear in gamma. And thus it has a solution. So let's go back to a slightly more general view on optimal transport, or OT, not in only the case of discrete distributions, but more generally. Let Pk be the space of probability measures mu, such that we have certain moment conditions. So those moment conditions, we mentioned them briefly before. They are here to ensure that the integrals we are writing are finite. So here we assume that there exists an x0 in the state space, such that the integral of the distance between x and x0 to the power k for a k larger than 1, larger or equal to 1, with respect to mu is finite. So here d denotes a ground cost, or a distance on the state space, on which the probability distributions are defined. So for example, if the distribution mu is a distribution on r to some power, we write the power dim, perhaps not to confuse it with the distance d, then the distance d might be chosen to be the Euclidean distance. The Euclidean distance is defined as d of x, y equal the square root of the sum over all the components of the square difference between xi and yi for component I. So if we employ this distance, or whichever other distance on the ground space, then for two measures p and q in this space pk, we defined the so-called Wasserstein distance, or Monch-Kantorowicz distance, wk pq, to be the infimum over all couplings gamma of p and q of the integral of the distance between x and y to the power k, integrated with respect to the coupling gamma, and we put this whole expression to the power 1 over k. So later on we'll consider the case k is equal to 1 and perhaps sometimes k is equal to 2. This we call the Wasserstein or Monch-Kantorowicz distance between p and q. So you recognize the optimal transport problem in the definition. And to continue the special case where p and q are continuous distribution on the real line R, what we've seen before is that the optimal transport is obtained for the coupling gamma star, obtained as the distribution of the inverse CDF transform of x and y applied to the same u. So that was our common random number strategy and the optimality of this strategy. And so in terms of gamma star here, which is not a map but a coupling, we call it either the optimal transport coupling or the optimal transport plan. So it's our plan on how to transport the mass of the distribution P into the mass of the distribution Q. So this object WK is a distance between elements of PK, this set of probability measures. So that's not obvious, but it's a classical result that it's distance between probability distributions. So it's non-negative. WK of P and P is equal to 0. That's easy. And what's less easy is the triangular inequality is satisfied. So the distance between P and Q is less than the distance between P and R plus the distance between R and Q. So all of those properties are satisfied for the Wasserstein distance WK. Let's comment on a special case. If we choose the ground metric or the ground distance d to be dxy is equal to 1 if x is different than y and 0 otherwise. So the indicator that x is different than y. In that case, the expected distance between x and y is exactly the probability that x is different than y. And so we recognize that the distance W1 between P and Q, this infimum over all couplings of this expected cost, is in fact the total variation distance between P and Q. So if the distance is different, then the Wasserstein W1 is different, but we retrieve the total variation distance as a special case of the optimal transport distance. It sounds a bit convoluted, but it is sometimes useful. Let's take another example. If d of xy is the Euclidean distance between 2 points in R to the power some dimension, we will see now some similarities and differences between the total variation and the Wasserstein distance. So let's take 2 points, x0, y0. And let's imagine first that P is simply a Dirac mass on x0 and Q is a Dirac mass on y0. So those are just two Dirac masses. So with probability 1, the variable following P is equal to x0. So the TV between those two distances, recall that it is defined as the supremum over all sets of the difference between the probabilities assigned to those sets. Here it will be equal to 1 for any x0 and y0. You can compute that to check. And on the other hand, the Wasserstein 1 distance between P and Q is exactly equal to the distance between x0 and y0. So we can do a little diagram. Pick 2 points, x0 and y0 on the real line. The distributions P and Q are Dirac masses on those 2 points. So in Wasserstein distance, the distance between P and Q is in fact exactly the distance between x0 and y0, which is perhaps intuitive. So you think those two Dirac masses are closer or not, depending on the distance between the points x0 and y0. So if we introduce a sequence xn going to a limit x, when n goes to infinity, then the Wasserstein distance between the Dirac mass on xn and the Dirac mass on x goes to 0. Whereas on the other hand, the total variation distance between any two Dirac masses at different points is always equal to 1. And so that's a quite different behavior. And we say that Wk, the Wasserstein distance, metrizes weak convergence. So that means that if a sequence of distribution converges weakly, then it converges in Wasserstein, which is not the case for TV. So Pn in general converges weakly to P. So by definition, this means that for all continuous bounded functions f, the integral of f with respect to Pn goes to the integral of f with respect to P. That's weak convergence. And so if you have this, and the two distributions Pn and P are in the space Pk, then the Wasserstein between Pn and P goes to 0 as well. So that's what is meant by Wk metrizes weak convergence, contrarily to the total variation distance. So on the other hand, there are also sequences that converge in total variation, but not in the Wasserstein distance. So for that, let's introduce Pn, a distribution that puts mass 1 minus 1 over n on 0, and mass 1 over n on n. The limit, we define it as P equal to a Dirac mass on 0. And then the TV between Pn and P can be computed, and it's equal to 1 over n, which goes to 0. And so Pn goes to P here, which is perhaps intuitive or reasonable. But on the other hand, W1 between Pn and P is equal to 1 over n times the cost between 0 and n. And so if you use the Euclidean cost, that's in fact equal to 1 for all n. So the convergence here occurs in total variation, but not in Wasserstein 1. Because the mass that escapes to infinity, even though it vanishes, but it makes the Wasserstein equal to 1 for all n. So you can have convergence in TV and not in Wasserstein, and vice versa. So to continue between the analogies between TV and Wasserstein, we can consider alternative representations of the Wasserstein K distance. So recall that the TV had a number of alternative representations. The starting point was the definition in terms of the supremum over a set A. But we've also seen that it was equivalent to the infimum over all couplings of the probability that X is different than Y. It was also related to the integral of the absolute value of the difference between P and Q. There was, I believe, a factor 1/2 in front of that to be checked. And we've seen also that in the lecture notes, a representation in terms of the supremum over all functions h bounded by 1 of the expectation of h of x minus the expectation of h of y, where x follows p and y follows q. So the total variation had all these different representations that are convenient in proofs, for example. In fact, likewise, the Wasserstein distance has some alternative representations. So we write the definition in terms of an infimum over all couplings. But if we focus on the case, for example, where the state space is R, the real line, so P and Q are distributions on the real line, then we can also write the Wasserstein K distance as an integral of the difference between the CDF of x and y to the power k and integrated over the real line. So instead of having an integration of the difference between the PDF, the probability density function, here we have the cumulative distribution function. In the general state space, but in the special case where k is equal to 1, we have also this representation of the Wasserstein 1 between P and Q as the supremum over a class of function. So here it's h Lipschitz with coefficient 1, which means explicitly that the absolute value of h of x minus h of y is less than the distance between x and y. So of course it depends again on your choice of distance. Of this supremum of, so then the difference in expectations. So it's similar to this total variation representation, but instead of functions bounded by 1, it's Lipschitz functions with coefficients bounded by 1. So we've seen also in the special case where the state space is the real line, an explicit formula relating y to x, achieving this optimal transport cost. So, in other words, optimal in terms of positive correlations between x and y. And going back to the Monte Carlo setting, this of course suggests a method to obtain a variable y following q if we have access to a variable x following p, because it suggests explicitly a transformation relating x and y. But what about the general case? Of course, in Monte Carlo, we are mostly interested in cases where the dimension is more than 1. In that case, optimal transport maps are rarely available, practically never, apart from discrete cases and Gaussian variables, basically. However, there are suboptimal transport maps, and in particular, there's one that basically always exists, definitely for all continuous random variables, called the Knott-Rosenblatt transform or transport map. So let's define it. Let x be made of d components, and likewise for y. And we write the first component, x1, following distribution p1. And we're going to denote by p1 also the CDF. Then x2 given x1 is p2 bar 1 given x1, and so on. And for y, we can write y1 follows q1, y2 given y1 follows q2 bar 1, and so on and so forth. So we decompose the joint probabilities into a marginal and a product of conditionals. Then we can define a transport map. So specifically, we define the first component y1 to be the inverse CDF of q1, composed with the CDF of p1 applied to x1. That's what we've seen before, but now we can go on with y2 define in terms of inverse CDF and CDF for the conditionals given y1 and x1 respectively, and that applied to x2. So that's just a function that we can apply to x2 to obtain y2. And you can see that it's a function of x1, y1, and x2, in fact. y1 itself being a function of x1. So really, y2 is a function of x1 and x2. And we can continue like that, writing yd, the last component in dimension d, in terms of inverse CDF and CDF transforms relating to the last conditional, so the conditional of the last component given all the previous ones, applied to the last component of x, xt. And so this way we define the vector y as a deterministic function of the vector x. And conceptually this can be done in a lot of cases again. In fact, you can also note that T is a triangular map, so evaluating its determinant might not be too complicated. However, in typical Monte Carlo scenarios, we do not have access to the marginal distributions. We might have the full conditionals as in a Gibbs sampler, but not the marginal of the first component, the conditional of the second given the first, and so on. And so there's extensive research in Monte Carlo to find maps T that are available and such that T of x roughly or exactly follows Q when x follows P. And also such that the determinant of the Jacobian is computed quickly, because that's going to be useful for the change of variable formula or for computing weights associated with those samples. You can see in the lecture notes reference to work by Marzouk, Reich, Heng, and Tabak, for example, which are very interesting works on this kind of Monte Carlo problem. So to sum up, what we've seen in this video are topics at the intersection between Monte Carlo and optimal transport. There are at least three very strong points of similarity between those two topics. The first one is common random numbers. We've seen that it exactly corresponds to optimal transport in 1D. Common random numbers combined with inverse transform sampling. But in fact, common random numbers are very classical in the Monte Carlo literature as a variance reduction technique. And you'll find things like control variates or antithetic variables in any book on Monte Carlo. So that's one common point between those topics. Second point is that transport maps can be seen as a generalization of inverse transform sampling, in the sense that transport maps are defined as maps that transform x following p into a variable y that would follow q. But then, of course, there are questions on how to find transport maps that are useful in the setting of Monte Carlo. We've just discussed this in the previous slide. So maps T that can be perhaps parameterized and learned from experiments. And the third point, that will be the most important one for us in the remaining part of the course, is that the Wasserstein distance, WK, can be used as a distance between probability distributions, and in particular we will use it to measure the distance between a Markov chain at time t and its limiting distribution. So we will use later on the Wasserstein distance as a way of measuring the distance of a chain to its stationary distribution. We will also use the total variation distance, but it will be convenient to have an alternative. We'll see for the analysis of some algorithms, it will be useful to have both. And so we'll see that starting from chapter 3. Okay, so today we've seen common random numbers, optimal transport couplings, and distances, such as the so-called Wasserstein distance. In the lecture notes, you'll find a bit more details, some special cases, such as, again, the multivariate normal distribution being treated in more details, and also a bit more references on the literature at the intersection between optimal transport and Monte Carlo. In the next video, we'll start looking at the convergence of Markov chains, in particular with a view towards Markov chain Monte Carlo algorithms. And so that will be corresponding to the first part of the third chapter of the lecture notes. In the meantime, have a great week.